Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Okay, so for this problem, I have a little setup of the problem we have here. We have two wires. One is flowing into the page, or the current of the wire is flowing into the page, and the other one on the right here is flowing out of the page. And we want to find the net magnetic field on the point P. So what we're given is we know the current in each wire is the same. So I1 equals I2. And just to be more specific, we can label these wires W1 and W2. So W1 is flowing into the page, W2 is flowing out of the page. And then we have our point P up here. We also know the distance between all three of these is the same. So the distance from wire 1 to P is the same, the distance from wire 1 to wire 2 is the same, and the distance from wire 2 to P is the same. So that tells us that we have an equilateral triangle here, which means that each side has to be 60 degrees, which gives you a total of 180. So each of these has to be 60. Because all these distances are the same, that means all these angles have to be the same, and they all have to total up to 180. So we know that each of these inside angles is equal to 60 degrees. So we can find the magnetic field from wire 1 with our equation for the magnetic field. I'm going to call it B1. We know that it's equal to mu naught, the constant, times the current, divided by 2 pi times the radius, which in this case is the distance d. So I will just put d. And that gives you the magnetic field from our wire up to the point, which is the distance d. So now we need to find the direction for this magnetic field. So that means we need to use our right-hand rule. And for the wire flowing into the page, W1, your thumb points into the page and your fingers will curl in the direction of the magnetic field, which in this case curls around the wire this way. And for wire 2, it's pointing out of the page. So you point your thumb out of the page and your fingers curl the exact opposite direction. So we can see from this diagram that our point is going to have magnetic fields pointing in this direction and in this direction. And because they're the same distance with the same current, they're going to be equal. So the next step we want to do is to break these up into components. So this one is magnetic field from wire 2, and this is magnetic field from wire 1. So I'm going to take the magnetic field from wire 1 and make a triangle out of it. So if I take the vector here from wire 1 and move it down here, make it a little bit bigger so we can see what we're doing a little bit easier. This is B1. Now, what we know here is that the line from the wire is at 60 degrees from the horizontal. So this angle is 60. We also know that the magnetic field in relation to where the current is flowing, the magnetic field is going to be perpendicular to it, which means that these two angles here have to total to 90 because this magnetic field has to flow perpendicular to the normal plane, which is the line that the distance here is following. So if this line were to continue on up here, that's the blue dotted line I have here, which is 60 degrees. So this has to be perpendicular, which is 90 degrees, which means 90 minus 60, this side has to be 30. And these are all in degrees. So we have this angle now. I'm going to write it again over here just because we're getting a little clustered. So we have this, and breaking it into its components, it has a right component and a down component. So we have, this line is straight horizontal, which means this is our 30-degree angle. This is B1, sorry, never labeled that. So that means this side is B1, and we have an X component and a Y component. But we know the other side is going to have a similar situation. So it's going to have, so we're going to, B1 again, keep this straight. So for B2, we'll have the opposite. We'll have a negative X direction, a negative Y direction, or we can just call down Y because we're not dealing with any upward Y components. So downward Y will be positive in this case. And then we have our direction is going to be pointing, actually, let's do it. We can move our vector because our magnetic field is going to point this way. So we're going to want our Y component to be here. And this is also 30. And this is our Y. So the X's are going to be pointing in opposite directions, which means we'll have a minus X plus a positive X. So the X components will cancel, and the Y components will double. The Y components are both in the same direction. We can see from this diagram, the X-ward directions for both are in opposite directions, so they'll cancel. Y will add. So let's deal with B1 first. So we have our diagram here. This is degrees. So now we know B1, and we want to know what this Y value is, which is the opposite of this angle, which means we probably want to use sine. So sine of 30 degrees gives you the opposite over the hypotenuse, which in this case is Y times B1. Or we can just move the B1, so this B1 would be under here. We can just move it to the other side in this step. So our Y is equal to B1, the value we calculated for this direction, times sine of 30 degrees. That gives you your Y value. But we have another Y value, and it's going to be exactly the same from the other wire, which means we multiply this by 2. So 2 times what we calculated for the first wire, sine of 30 is equal to your Y direction for both wires, or your Y component of the magnetic field for both wires. But sine of 30 degrees is 1/2, so it will end up canceling with the 2. So the sine of 30 degrees cancels with the 2, which means our Y component actually, just to be a little bit more specific, I'm going to call it By because it's a magnetic field component. Our Y component of the magnetic field, which is the total net magnetic field, is equal to what we calculated for one wire. Now you can choose B1 or B2, it will give you the same answer here. I wrote a 2 as I was saying 2, but we did B1. So our total net magnetic field is equal to the magnetic field due to one wire. And that's simply because the sine of 30 is equal to 1/2, which cancels with the 2. Otherwise, we'd have double our value, sine of 30. And that will give you your answer.